So in this fragment, what we're covering is how do we use second order derivative to find point of inflection, uh, and checking for max or min points. So what I'm going to do is I'm just going to demonstrate a simple curve sketching here. Now, in this fragment here, when I look at, suppose this is the function. Now, what I'm going to do is first I'm going to sketch my single derivative curve. So I'm going to take, let's say, a single derivative curve sketching. So this part, these are going to be the roots of the derivative curve. Now here the slope is negative, then here slope is positive, and here it is negative. So in this case, your derivative graph is actually is going to be below x-axis till a, between a and b you can see it is positive. So here it is going to be above x-axis, and then here again below x-axis. Now I'm going to consider my um, next second derivative graph. So now I'm plotting second derivative. So my first derivative, wherever it cuts the x-axis, wherever it is maximum, will cut the x-axis. Now you can see that if I draw the sign diagram of single derivative and double derivative here, this is my single derivative, and I'm going to draw the double derivative as well. So when I look at the critical point here and project these points, so here it is negative, positive, and negative. Here it is negative, sorry, positive, and here it is negative. So you can see the slope of the green curve is negative, positive till this point, till point C, and after that it becomes positive, negative slope. So positive before C and negative after C. Now, there's an interesting way to obviously conclude some of the things. Now, if I look at here, the derivative will be something like this. This is how the second order derivative curve will look like. Now, coming back to some of the conclusions, like if you look at if the curve is actually if it's minimum at this point is minimum. Now, at minimum, your derivative firstly is 0. At minimum, your derivative is 0. And if I look at the double derivative, it's positive. So this is very interesting. So we just did like maxima minima concept. So you're going to do dy by dx, first equate to 0. You solve for x, and you can input this x value in double derivative. And if double derivative comes positive, it's a minimum point. You can clearly see that if I look at the derivative is 0, and now this gives me another way to verify whether it's a maxima or minima. Simply, now you can look at the other aspect also. If I look at my minimum point, which is here, sorry, this is the maximum point, my derivative is 0. So my derivative is 0. Clearly, you can see below that point, derivative green curve attains a 0 value. Okay, so for minimum, my derivative is 0, of course. And then you look at the maximum, look at the double derivative value. It's coming negative. It's below x-axis, cutting y-axis at negative point here. So you can see that your double derivative here is negative. So if I get after solving derivative equals to 0, you input in double derivative, and if double derivative comes positive, and then this is double derivative comes negative, it is the maximum point, local max point. So this is something which is very interesting if you look at to find out the maxima and minima. So I'm going to take an example after this, but just to debrief, what about how to use double derivative to check if it's maxima or minima. So you're going to first find out straight away, the dy by dx, then you find out where it is 0, solve for x, and then you input in double derivative. If it is positive, it's a min. If it's negative, it's max. And there can be a question that, okay, what if it is 0? What if it is 0? Now that is the part which I'm going to cover up as a point of inflection. So as far as point of inflections are concerned, that this is something which we need to touch base upon. So now I'm going to take, let's say this is the same curve as the previous one. Now the derivative was like this, and your double derivative was at this point you had minimum, and at this point your double derivative looked like something like this. So we're going to talk about something called as a point of inflection. Now, point of inflection is, if you notice, actually it is naturally the curve would have been something like this. So if you look at, this is the point of inflection about which the concavity change. Now you can see this is till here, it is concave up, and after this point of inflection, it's concave down. So this is the point I'm talking about. Now, if you look right below that, the double derivative is 0. So guys, for point of inflection, now this is very interesting topic. For point of inflection, what you're going to do is follow the procedure. Inflection, you're going to straight away equate double derivative to 0. So my double derivative will be equated to 0. Now, this is not, this doesn't mean that, okay, it is guaranteed point of inflection. There are some cases which I'll talk later on about where the point of inflection can be basically deceiving. Like even the double derivative is 0, it's still not the point of inflection. So what is important is, now if you look at before this point of inflection, in this part, which is here, the derivative, double derivative is positive, for which it is concave up. So for double derivative being positive, if double derivative is positive, it's concave up. And if double derivative is negative, it's concave down. So concave down. So in that case, what I'm going to do is, after you solve for x, I'm just going to quickly draw the sign diagram for this point for double derivative. And if sign diagram is either positive negative or negative positive, that is going to confirm it is a point of inflection. So if the signs are not the same, now remember the double derivative tells us the possible point of inflection. So concavity has to be different, and my concavity is decided by double derivative. So that's why it is important that the signs are different. One side is positive, other side is negative. One side is negative, other side is positive. And if signs are not the same, then it is not a point of inflection, even though double derivative is 0. Now, there is another interesting thing is that how do I check if it is a stationary point of inflection? There are two types of point of inflection. So I did, let's say, okay, double derivative equals to 0. I got some x coordinate. Okay, I verified with sign diagram of double derivative till here. Okay, now I got, okay, it's positive, negative. It is confirming me its point of inflection. But now some case, what happened is that even at this point, x equals to a, if I input in single derivative, my answer comes to 0. So it means that in that context, it is a stationary point of inflection. Now, stationary point of inflection actually look like this, something like here. So you will have like a flatness in the curve, and then it can go like this. So here approximately is a stationary point of inflection. And non-stationary point of inflections are something like this. Here you can see it's concave up before this, and before that, after that, it's concave down here. So at stationary point of inflection, your derivative and double derivative both are actually 0. So at a stationary point of inflection, I'm going to take one example that demonstrate this concept. So let's say if I have x cubed minus 4, this is my function, and I'm going to finding out the point of inflection. So I'm going to do dy by dx, that's your 3x squared. I'm going to find double derivative after this. So double derivative is 6x. I'm going to solve for 0. So I get x as 0. Now, since I got x as 0, I'm going to check for it is whether it is sign diagram and changing or not. So if I plug x as 0 here, now if I plug x as 0, what I'm getting is, let's say the sign diagram is, if I say -1, if I plug in this, it is negative here and it is positive here. So this side it is like concave up, and this side it is concave down. So that is confirmed it is point of inflection. But now what we have is, if I want to check whether this is a stationary point of inflection or not, you're going to plug this x coordinate 0 in the single derivative. And what we notice is that yes, the single derivative also comes to be 0. So that's where it is a stationary point of inflection. And if this would have been non-stationary, this would be non-zero. The single derivative will be non-zero. So I hope this is clear. Now let's take an example that I took in the previous segment. That was x cubed minus 3x in order to check all the key concepts. So dy by dx, it is going to be 3x squared minus 3. I'm going to solve it for equals to 0. I'm going to check x squared minus 1 equals to 0. So it gives me x is plus minus 1. Now find out the double derivative. The double derivative comes as 6x. Now if I input x as positive 1, I get double derivative is coming as positive 6, which is why at x equals to 1, there is a minimum. And when I put x as minus 1 in this, I get double derivative equals to negative 6, which is less than 0. So that's why x is minus 1 is a maximum point. So it's like this. Now, so far, the context that has become clear to me is, okay, at minus 1 and plus 1. At minus 1, there's a max, and at plus 1, there's a minimum. So I really don't know the y coordinate. So I'm going to find out the y coordinate as well. If I plug x as 1, I get the answer as 0. So if I plug x as 1, my y coordinate is 0. And when I plug x as minus 1, my y coordinate is negative 1 here plus 3. So negative 1 plus 3 is going to be positive 2. So at x equals to minus 1, y is positive 2. So somewhere here is negative 1 comma 2, and this point is here. So far we got till that point. Now I'm going to find out where is the point of inflection. So for point of inflection, equate double derivative to 0. So double derivative, if I equate to 0, I get 6x equals to 0. I get x is 0. Now just check with the sign diagram of double derivative. So double derivative sign diagram. Now I'm going to check here is 0. If I put a point in the left side, it is negative in the double derivative. And if I put here, let's say 2, 6 2s are 12, I think it's positive. So it's this side's concave up and this side's concave down. Okay, so let's check out. So concave up. So at 0, my y value is also 0. Okay, so now when you look at the curve here, it's actually going to be something like this. So concave down. So concave down here. And after 0, it is basically becoming concave up. So from this point, it's becoming concave up. So maybe when I look at 1, oops, at 1, my y value was actually negative 3. 1 minus 3, that's here, negative 2. So not 0. So it's actually like here passing through 0. And after that, it comes like this. So you can clearly see that this is a maximum point. This is a minimum point. And at 0, there's a concavity change. Now, if I plug 0 in the single derivative, it doesn't become 0. So that's where it is non-stationary point of inflection. So I hope it is clear now about the point of inflection criterions. Just to summarize, the point of inflections are referred as the points where the concavity change. So for that, you're going to do derivative, double derivative equate to 0. You solve for x and then draw the sign diagram. For the double derivative, if sign diagram is positive, negative, negative, positive, it's a max. I mean, it's a point of inflection confirmed. If you wish to check whether it's the stationary point or not, it is going to be plugged in single derivative. Single derivative is 0. It is confirming that it's a stationary point of inflection. So that's how you do the maximum minimum point of inflection. And I hope it is clear now.